Hi everyone. Today we'll be talking about our project, Learning-Aided 3D Semantic Bayesian Kernel Inference for mapping. The problem that we wanted to address was how to construct a dense semantically labeled 3D map purely from a point cloud and odometry in dynamic environments. The reason why this matters is that motion planning and scene interaction tasks in robotics often benefit heavily from having a high definition, dense semantic map. We chose to use LiDAR scans because they provide geometric information at high speed with high precision. However, because these scans often provide sparse point clouds, they require additional post-processing to extract meaningful semantic information. In addition, we wanted to make sure that our method was robust to dynamic objects in our environment.
For the current limitations, the Bayesian kernel inference mapping assumes that we are working on a static environment, and also there are some undesired effects such as leaving traces of the dynamic objects. The learning-based solutions often pose a computational bottleneck for operating frequency and do not accurately represent the uncertainty of the true map. Recent works in dynamic Bayesian semantic mapping offer an efficient closed-form solution for estimating the world state with uncertainty. We plan to extend these works to generate a global continuous semantic map. Here's a highlight of our solution. We replaced the autoregressive model with a neural network, which is called MotionSC, to predict semantic egocentric map. We also modified BKI to directly work on the softmax value output from the neural network for updating global map.
For the dataset, we used the Color SC dataset, since one of our main goals was to handle the dynamic cases well, and the semantic kitty dataset has intrinsic traces. We loaded the validation dataset and ran the forward pass of the trained MotionSC model on Google Colab, saving the softmax values for each frame. We processed the softmax value, and these slides showcase the intrinsic problems of the semantic kitty dataset. By comparison between a Color SC and semantic kitty, as you can see in this figure, Color SC gives us a trace-free, occlusion-free dataset, which enable us to perform dynamic mapping easier.
So here's an overview of our system architecture. First, we utilize a Carla data loader to read in the LiDAR scans. Then we run the forward pass of the MotionSC model on Colab to generate softmax predictions. Due to the computational limitations mentioned earlier, we save the softmax predictions to a file. Later, we read from these files and publish the predictions to a ROS topic and receive them in our BKI code for further processing. Now we're able to integrate the scans and data from each egocentric frame and add it to our global semantic map. And so here we will be showing you some of our results. And something to note is the yellow represents barriers, the purple represents sidewalks, the pink cars, and the orange is trees. And something to note is that the trees look cut off, and that is due to the neural network only predicting up to a certain height. And here's a video of our results.
In order to have a quantitative comparison, we chose to analyze the Jaccard score performance. Since free space is represented implicitly, we chose not to represent it. Compared to the performance of semantic BKI, we can see that our model had better agreement with the ground truth over all classes. Furthermore, semantic BKI has high scores to begin with, since it is using MotionSC rather than the autoregressive model, which highlights the boost in the performance due to our novel approaches. Finally, we want to point out a few limitations we came across. The performance was bottlenecked by our hardware and the BKI lever, and we saw that processing each frame took around 1.25 seconds. This would translate into 0.8 frames per second, which is not enough for real time. However, our performance can be improved drastically with better hardware, especially by utilizing a GPU. We also saw erroneous traces of cars towards the end, and this can be attributed to the neural network getting overly confident. A possible improvement would be to not rely on the predictions, but to rather account for the uncertainty in the BKI layer. Here are our references, and thank you for your time.